Hi everyone, I will be presenting the work submitted to DCASE 2021 workshop entitled Low Complexity Acoustic Sync Classification for Multiple Device Audio Analysis of DCASE 2021 Challenge Systems, done with Toni, Heittola, Annamaria, Mesaros, and Tuomas Virtanen. I will start with the motivation behind this work, followed by the dataset, baseline system, and setup of the task. Then I will present the challenge results with a special focus into features, architecture, and system complexity. Finally, I will conclude with a discussion. What motivated this work is how the performance of the acoustic sync classification system gets affected by mismatches between training and testing data, while at the same time real-time applications require the use of low complexity system to operate on devices with limited computational capacity. This leads to merge both problems, which have been addressed independently in previous challenges, setting a more challenging scenario to be addressed by the audio research community. In this figure, we can see illustrated the problem of classification of acoustic sync from different recording devices. In real-life scenarios, we have to deal with data collected from devices not available during training and with devices with limited computational capacity. The dataset used in the task is Tower Urban Acoustic Sync 2020 Mobile. Comprises recordings from multiple European cities, Amsterdam, Barcelona, Helsinki, among others, and 10 acoustic syncs such as airport, shopping mall, metro station. The recordings are done using 4 real devices, A, B, C, and D, with 11 additional devices simulated using the audio from device A. There are in total 64 hours of audio available for the development set and 22 hours in the evaluation set. The baseline system consists of a fully convolutional neural network. The input for training the network is calculated using 40 log Melban energies with analysis frame of 40 milliseconds and 50% hop size. In order to fulfill the model size limitation, the model parameters are quantized to 60 bits using Keras backend in TensorFlow after the training. Previous year challenge had a model size limit of 500 kilobytes. Now it has been dropped to 128. This limit allows 32,768 in float 32 representation, which is often the full data representation. The computational complexity of the feature extraction stage is not included in this limit due to the lack of established methodology for slow feature extraction implementations. However, in the case of using embeddings, then the network used to generate those counts in the calculated model size. The system performance evaluation is done using multi-class cross-entropy and accuracy, where accuracy is calculated macro-average, meaning average of the class-wise performance for each metric, but because the data is balanced, this is equal to the overall accuracy. Multi-class cross-entropy is used for ranking the systems, in order to create a ranking independent of the operating point. Thus, accuracy values are provided for comparisons with the methods evaluated in previous years. The table shows the class-wise performance of the baseline system on the development dataset. The task received a total of 99 submissions from 30 different teams, which shows how the task remained a popular one in the challenge, despite the increasing difficulty of the setup. The most used techniques are residual networks and weight quantization, with most of the submitted systems outperforming the baseline. The confidence intervals for log logs was calculated using jackknife estimation. In this table are displayed the top 10 teams' best system of each team, ranked based on the log logs. If systems will be ranked by accuracy, their order will change. For example, the 3rd top ones will keep their spot, but teams 12th and 17th will move up a bit. The highest accuracy for the classification was 76 96.1% for the system of QTI. Regarding features, all top 10 teams use mail energies. 3 out of 30 do not use log mail. Instead, they use other ones like gammaton, dith scattering spectrum, and embeddings, for example, like IMNet. Augmentation techniques are used also, like mix-up, used by 20 teams, and spec augment by 10 teams. Other techniques are commonly used to improve the performance of CNN networks. The most popular architectures are the residual models. In fact, a total of 15 teams use them. The exception is the second best team, which uses ensembles of CNN, and the ones below baseline, which make use of fully convolutional networks. Some models that consider processing power and memory constraints are MobileNet and EfficientNet, which are networks based on residual blocks. A total of 5 teams use some modified version of such models. The top 10 systems belonging to 3 different teams are close to the allowed model size limit. They range from 110 to 126.81 kilobytes, with the model ranked first having a size of 121.9 kilobytes. The smallest model can be found in position 77, which uses a filter planning strategy consisting of 3 steps, with 1 extra for final quantization of the weights to 16 bits. Sparsity, used in combination with quantification, is a very popular and efficient way of reducing the model size. All systems have better performance on the devices seen during training than on the unseen ones. The difference is almost 3% statistically significant, while for seen and unseen cities, the performance does not vary that much. Indeed, some systems get better performance for unseen cities. The mismatch due to unseen devices is more challenging than the mismatch created by different cities due to the different properties of the recorded audio. Purest performance is related to device D, which is the GoPro. This work studied the results for the DCASE 2021 challenge, task 1A, low complexity acoustic scene classification with multiple devices. The task combines the needs for robustness and generalization to multiple devices of such systems with the requirement of a low complexity solution. Residual networks have been shown to be the most efficient regarding acoustic scene classification for complexity constraint solutions. Although quantification combined with sparsity techniques have shown to be the most efficient and popular ones for reducing system complexity, model architecture and other learning techniques, such as focal loss and knowledge distillation, must be considered in order to achieve good classification performance. To conclude, we have seen how the popularity of the task shows that acoustic scene classification is still relevant for the audio community, and in particular, to the development of solutions applicable for real-life devices. Thank you, and I'm looking forward to see you all in the DCASE workshop.